Section 5.1 Angles and Radian Measure. An angle is formed by two rays that have a common endpoint called the vertex. One ray is called the initial side, and the other ray is called the terminal side. Greek letters such as alpha, beta, gamma, and theta are often used to label our angles. An angle is in standard position if its vertex is at the origin and if its initial side lies along the positive x-axis. Positive angles are generated by counterclockwise rotation, and negative angles are generated by clockwise rotation. An angle is called a quadrantal angle if its terminal side lies on the x-axis or on the y-axis. Angles are commonly measured by using degrees and looking at the amount of rotation from the initial side to the terminal side. A complete rotation of the circle is 360 degrees. We have some special angles we want to learn. Acute angles measure less than 90 degrees. Right angles measure exactly 90 degrees. Obtuse angles measure more than 90 but less than 180. And finally, straight angles measure exactly 180. Sometimes we'll need to measure angles using radian measure. An angle whose vertex is at the center of a circle is called a central angle. The radian measure of any central angle of a circle is the length of the intercepted arc divided by the length of the radius. 1 radian is the measure of a central angle of a circle that intercepts an arc that's equal in length to the radius of the circle. Consider an arc of length s on a circle with radius r. The radian measure of that angle is given by s divided by r. In this example, we have a central angle theta in a circle of radius 12 that intercepts an arc of length 30 feet, and we want to find the radian measure of theta. We use our formula, theta equals s over r, so that gives us 30 feet over 12 feet. The feet can cancel, which reduces to 2.5, and this is measured as 2.5 radians, so the radian measure of theta is 2.5 radians. Sometimes we'll need to convert between the two ways of measuring angles. We'll use the basic relationship that pi radians equals 180 degrees. To convert from degrees to radians, we'll multiply by the fraction pi radians over 180 degrees. To convert radians to degrees, we'll multiply by the reverse fraction, 180 degrees over pi radians. Since pi radians equals 180 degrees, both of those fractions are equal to 1. Anything over itself equals 1. When we multiply by one of these fractions, we won't be changing the value of our angle, we'll just be changing the way it looks. Here are some examples. For 60 degrees, we'll multiply by pi radians over 180 degrees. The degrees cancel, and we get 60 pi over 180 degrees. Since 60 goes into 60 once and into 180 3 times, that will reduce to pi over 3 radians. For 270 degrees, again, we'll multiply by pi radians over 180. The degrees cancel, and this result can be reduced because 90 goes into 270 3 times and into 180 twice. We get 3 pi over 2 radians. For this example, we'll again multiply by pi over 180. The degrees cancel, and to reduce this result, we recognize that 60 goes into 300 5 times, and 60 goes into 180 3 times. So we get negative 5 pi over 3 radians. Now let's take a look at converting from radians to degrees. In this first example, we'll rewrite it with the radians up top, and then we can multiply by that special fraction. Remember, these fractions are equal to 1 because the top equals the bottom. And we put radians on the bottom because that's what we want to cancel. In fact, the pi's will cancel and the radians will cancel, giving us 180 degrees over 4, which reduces to 45. In example B, again, we'll rewrite it with radians up top, multiply by 180 over pi, and the pi's cancel, radians cancel, giving us this, which works out to negative 240 degrees. Finally, the 6 radians, you can think of it as 6 radians over 1. It doesn't have a pi in it, So when you go to cancel, only the radians cancel, giving us this. And then typically we'll approximate that using the pi button on our calculator, which comes out to about 343.8 degrees. This figure illustrates that when the terminal side makes one full revolution, it forms an angle whose radian measure is 2 pi. Here we see 3/4 of a revolution, 1/2 of a revolution, and 1/4 of a revolution. In example 4a, we're going to draw and label our angle alpha in standard position. The angle is positive, so we're going to rotate counterclockwise. And we have 3 pi over 4 is 3/8 of a full rotation of 2 pi. Notice that the 8 and the 2 would cancel to give us the 4, so this is a common way to write it so we can see what fraction of a full circle we're going to go. Remember that there's 4 quadrants, so if we're going to break this up into 8, then each piece would be 45 degrees. 1, 2, 3, 4, 5, 6, 7, and 8. And we need to go 3 of those from our initial side. So 1, 2, 3. And we'll put our terminal side in that location. Here's a tip that might help you reduce your computations. Since 2 pi is all the way around the circle and pi is halfway around, we can avoid this computation and just use our angle directly. Pi is halfway around the circle. We're breaking that half of the circle up into 4 pieces, and we're moving 3 of them. So half the circle broken up into 4 pieces. They're still 45 degrees each, and we're going to move 3 of them. 1, 2, 3. We end up in the same place. Example 4b is asking us to draw and label angle theta. Since it's negative, we're going to rotate clockwise. Then you can take the absolute value to avoid dealing with the negative. Pi over 4 is 1/8 of 2 pi. 1/8 of the full circle. We're going to go 1/8 of a full revolution in the negative direction. So from our initial side, 1/8 of the circle is going to be 45 degrees because you're going to be breaking this up into 8 pieces, and we're going to go 1 of those in the negative direction. So there's our terminal side. We can use this tip again. Instead of thinking of it as 1/8 all the way around the full circle, we can go to our angle directly. Pi is halfway around the circle. We're breaking up that half into 4 pieces, and we're going negative 1 of them. Note that since no coefficient is shown here, the coefficient in front of pi is assumed to be 1. This next example, angle beta, it's negative, so we're going to go clockwise. We take the absolute value if we're going to just remember that we're going clockwise. And 5 pi over 3 is 5/6 of a full rotation. Again, you can notice that the 2 and the 6 would cancel, giving you your 3. So this is equivalent to our original angle. We're going to rotate 5/6 of the circle in the negative direction. So from our initial side, we have to know what 1/6 of the circle is. Each of them is going to be about 60 degrees. 1, 2, 3, 4, 5, 6. And so we need to go 5 of those in the negative direction. So from here we'll go 1, 2, 3, 4, 5, and we'll draw our terminal side through that value. Same tip as before. 2 pi is all the way around the circle. Pi is halfway. So we can go directly after our angle by recognize that pi is halfway around the circle. We want to break that up into 3 pieces. So halfway around the circle broken up into 1, 2, 3 pieces. And we want to go negative 5 of those pieces. So 1, 2, 3, 4, 5. For our next example, we're going to be looking at gamma, which is 7 pi over 6. It's a positive angle, so we'll go counterclockwise. 7/6 of half the circle is 7/12 of the full circle, if that's the method you prefer. We're going to go 7/12 of a revolution in a positive counterclockwise direction. So from the initial side, we need to break this up into 12 pieces. If we break the circle up into 12 pieces, they're 30 degrees each. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we want to go 7 of those in the positive direction. 1, 2, 3, 4, 5, 6, 7. So we'll draw our terminal side through this value. Using our trick, if pi is half the circle and we break that up into 6 pieces, they are still 30 degrees each. 1, 2, 3, 4, 5, 6. So we want to go 7 of those little pieces, and that's still 1, 2, 3, 4, 5, 6, 7, takes us to the same terminal side. So there's many common angles that we see in trig. They're usually ones that are multiples of 30 degrees, 45, 60, etc. And in terms of fractions, in radian measure, pi over 2, 3, 4, 6, those are some of the most common ones, and you can see them listed here. You don't want to memorize them all, but you will need to get comfortable with them. And so if we just look at a few, if I was looking at the quadrantal angles, I go from 0 to 90 to 180 to 270, and then we would come back to 360 or 2 pi. This chart shows them in the negative direction. If you're going to spend some time learning them, I would say learn the ones on the other chart, and then when you need to reverse the direction, just adjust it based on the negative. This is a chart that shows a lot of the common fractions of a revolution that we would be interested in. Let's take a look at one. For example, 1/8 of a revolution is 1/8 of a full circle. In terms of radians, 1/8 of 2 pi is pi over 4. In terms of degrees, 1/8 of 360 is 45 degrees. And there's more of these. So you can take a look at these fractions. For instance, 7/8. 7/8 of 2 pi. The 8 and the 2 would cancel. We get 7 pi over 4. Or 7/8 of 360. That works out to 315 degrees. Coterminal angles are two angles that have the same initial side and the same terminal sides, but you may arrive at that terminal side using different rotations. Here's an example of 90 degrees that we rotated through the positive direction, but we could also get there by going negative 270 degrees. These two angles have the same initial side and the same terminal side, so they are coterminal angles. With coterminal angles, if you increase or decrease by a full rotation, which is 360 degrees or 2 pi radians, then you're going to result in a coterminal angle. Saying this algebraically in degrees, if you have theta degrees and you add or subtract any multiple of 360, so k needs to be an integer like 1, 2, 3, or -1, -2, -3, every time you spin around the circle 360 degrees, you're going to end up in the same place as you started with your angle theta. In radians, it's the same idea. You actually will see this one more often because they prefer to do these types of problems with radians. So remember, 2 pi is a full rotation. If you have an angle in radian measure and you add or subtract a multiple of 2 pi, then you're going to still get a coterminal angle. Here's an example. We have a 400 degree angle, and they want us to use a coterminal angle that is positive but less than 360. So we'll need to take our 400 degrees, which is more than 360, and we subtract 360 degrees, and that gives us 40 degrees. So 400 degrees is coterminal with 40 degrees. Now let's look at negative 135 degrees. Again, we want to end up with a positive angle that's less than 360. So to make this angle positive, we're going to have to add 360. When we add 360, we get 225 degrees, which is a coterminal angle that's positive but less than 360. So negative 135 degrees is coterminal with 225. In example 6, we're going to look at a couple examples where we do this in radians. So if we have 13 pi over 5, that's more than 2 pi, so we'll have to subtract a full rotation from our angle. So we take 13 pi over 5 and subtract 2 pi. Now with degrees, it seems simpler. With radians, we're going to have to get a common denominator. So 2 pi is 10 pi over 5, so you can see the 2 there, the 10 over 5. But this allows us to subtract 13 pi minus 10 pi is 3 pi all over 5. Example 6b, we have a negative angle in radian measure, so we're going to have to add a full rotation of 2 pi. Our negative pi over 15 plus 2 pi, we rewrite that with a common denominator, so 2 pi is 30 pi over 15. So then the negative pi over 15 plus 30 pi over 15 gives us 29 pi all over 15.